Anyway, I think because we have a lot of students in our courses, uh, actually there are some surveys that still going on, whether we will have online courses or offline course. But because we have a lot of students, uh, uh, density of the students in the class, because it's still large. So for a course like this one, like who has, I think our students is around 40 to 50 students. I think it will be difficult for online, for offline class. So we will still have online lecture for for one semester. But for the exam, we can have offline exam, especially for the final exam. Okay, so that's just information, but I'm not sure whether the school will announce all of that information. But just wait, the official informations around October 5th or 6th, there will be a new announcement. Okay, that's about the courses. So for course like my course, like calculus one, because too many students, still we need to have online lectures. Okay, but for exam, we can have a physical exam, offline exam. So I think that will be on the final exam. Okay, for me. So all the exam aside from the final will be conducted online exam. Okay. All right. We can start. I'm just reviewing what we have done last week. Okay, let me go from the very beginning about calculus. We learned about functions, right? Okay. Oh, you want to scan the QR code? Yeah. Well, wait a little bit. I will move back. Okay. Just wait. Right. Okay. We learned about the functions. We learn about functions. What does function means? How we are going to use functions for. Okay. And then we develop the definition of a function, rule to assign each element in a set of, we say D in this definition, exactly one element called f of x in a set of element of E. And we can represent function as words, graphs, table, algebra. I think this is just trivial things, not necessarily all need to be remembered, but at least you know the concept. Okay, so we learn about domain, we learn about range, how to write domain, how to write range. Although I'm still haven't given you more details, but I will give you more later. And then we learn also, this is actually not one-to-one functions. I haven't told you about that yet. This should be just check whether it's a function or not function. Okay. Okay. So I didn't mention this last week. So if you see any functions and you want to check whether it is a function or not, what you can do is you can bring this line test. Okay, this is line. Okay, the vertical line test. Vertical line test. Okay, so you can make any line. Actually, you can make from here, from here, from here, any way you want. But it is to check whether you are going to cross the function once or more than once. If you cross more than once, like this one, it means that this blue line here, the curve here, is not represent function. So it's not one-to-one. Sorry. One-to-one is different case. Not represent a functions. Okay. And then we also have these piecewise defined functions that um, we can represent functions, not only one curve, but more than one. Okay, and we can have like this one. We have a linear, we have a quadratic, and we have more. We can have more. Okay, and we can have also even an odd functions, right? So the definition is this last part here. I hope you remember this. Okay, so whenever you put the negative variable, if it is going to be the original functions, the positive one, it's even function. If it is going to be negative, then it will be an odd function. Okay. And then we learn also, this is just example. I hope you try this. Okay. And then, yeah, pretty much that is what we have done last week. So I will move on to another session. And this is also last week. Okay, this is calculus in your words, what you have been thinking, what's your relationship toward calculus, right? Um, some is positive, some are negative. I hope I can make it enjoyable for you. Of course, the content itself, I must admit, it is quite a lot, and some, if you are not really pay attention or not really focus on study, you will be missing something, and then you will feel, oh, it's really hard. But if you are um, you manage your time efficiently, study, and then you feel happy, that's important. I think you can at least you can understand what the concept in calculus is. Okay, and then some of you are expect something here. I already read all of them. Okay, yeah, I hope I can meet your expectations. Yeah, and then some of you are asking, do you draw? Yes, I'm drawing all my stuff that you have been seeing, like the cartoon. Yeah, that's my drawing. Yeah, you some of you are wish to get not to pass the course to pass the course. So I hope you guys can pass this calculus. Okay. All right. So this is the QR code. If you want to scan again, okay. So you can please scan the QR code. We'll give you a few minutes, maybe 1 minute to scan, and we can start the course. All right. Okay. Let's start with this one. I have two picture here. So let me make it here. Okay. So determine the curve, both curves. Okay, the top and the bottom. Determine whether it is a function or not. If it is a function, what is the domain and what is the range? Okay. So first, if you want to tell whether it is a function or not, you can use the vertical line, right? So the first one, it is a function or not? It is function. This function. Anyone disagree? Is a function or not? All right. Yeah. How about the second one? It is a function or not? Not a function. Not a function. Okay. All right. All right. Good. Good. Second one is not a function. So for the first one, can you tell what it what is the its domain and range? Can you tell? Okay, and about the range. So if you are confused on reading this table, you can put the number here, -2, -2, -3. 2, 2, -1, -2, -3. Okay. All right, so if you see from the x-axis, which is we are going to look for the domain, we get the -3 here, right? And we get 2. There's nothing wrong in here. So all of the x along the -3 to 2 will be its domain, right? So we can write domain, you can write this. And how about the range? Now the range, we can observe the y-axis from -3 here, and then up until around probably here it is the number 3. But if you look at the range from the function here, please check this. We have this gap, right? And that's the thing that we need to be careful for. Okay. We need to write the range from -3 to -2, but -2 is an open interval, so we need to write. And then we continue. The other one is from -1. It's inside until the 3. Three is okay. Union. Okay. Okay. Yeah, Rion. Yeah, careful. Okay. In the limit, okay, if you look for a chapter 2 limit, most of the time at the early beginning of chapter 2, we will see more and more this type of conditions. Okay, you will see like a gap, and we call this gap as a discontinuity. Yes, jump discontinuity. There is several discontinuity, but I will tell you later. Okay, I will tell you later about this continue and discontinue. We will look for after we going inside the limit. Okay, now here the second part here, it's not a function because when you deal with this, right, with this line, you get this, this, and this. So we get three intersections, right? Then we can conclude that it's not a function. Okay. Okay. All right. Just wait. All right. Okay. Any questions? I think not too confusing for you. Maybe just a little bit additional things. If I have this A, B, and then C, and then D. Okay. If this is a function, okay, of course, to look at, it's a function. It's passing all the vertical line tests, right? If you look at here and see that from A to B, we get increase in y-axis, and then decrease, and then increase. So I just want to make sure that you understand that a function, okay, is called increasing on interval. Let's say interval I interval. if, okay, of course, it's lower than the next x, right? The second x. Whenever, okay, whenever the previous x is less than the next x, okay? And it will be same, decreasing on interval I if whenever, or make it the same with different, okay. All right, just additional information. Okay, let's move on to okay, any question here? I think no, right? Let's move on to the other section. It's called the transformation. Okay, transformation of function, or usually you call the from old function to new function. Right. I believe you have learned this at least maybe junior high, or maybe, yeah, I think junior high. Okay, so first look at the middle part. Okay, this one. So what I'm going to do will be, we are going to move this function, move or shift upwards, downwards, shift to the left, shift to the right. Okay, and this is just a review for you. Look at this is a function. Okay, we move upwards, we plus the function. Okay, because we are going up, the y becoming larger and larger, right? And going down, we minus with the constant, and it's going to be decreasing, decrease, right? Shift it downwards, shift downwards. Okay, and then we move to the right, and careful, sometimes you mix the minus and positive. This is x minus c. Okay, so this c is the distance you move your function, so you're becoming x minus c. Okay, and going to the left, it's x plus, okay, plus c. Okay, right? Do not get mixed with x and y, because sometimes you wrote, okay, you shift to the right, and then you write f x plus c. Okay, it should be minus, okay, for x. It should be minus to the right and then plus to the left. Okay, that's the first case. We call this also translation, the movement, okay. Shifting the function, right? Another one, look at the function here. This is the original one. Okay, the black one here. Okay, what happening here is we multiply the function with a constant. Okay, so c is a constant. C is can be greater 1, or can be less than 1, or in this case in 1 over c, like this one. So if we multiply with c, of course it's going to be scaled up, right? Scaled up. So scaled up. The scale is getting larger, but it's still a proportional, right? You see this peak here still have the same property, same behavior, but it's different scale. Like when you are, I don't know. I believe some of you are liking to design something, right, in your laptop, like maybe using Photoshop, Illustrator, or something similar to that, or just drag and drop in Words file, and then you put some picture, and then you are click the picture here, and then going to have the picture bigger, and then you try to tweak something, and then maybe you bring some filter, right? But sometimes in those apps, you can have like uniformly scale, or you can have a free form. So you can stretch maybe your photo and your face becoming like this. This is your face, right? And maybe you can make some funny effect for that, right? So here, when you are seeing this, it's similar. Okay, like you are stretching the functions, right? You stretch the function and it's become like this one, and it's equal with the constant here. Okay, equal with the multiplying the constant. And when you're scaling down, so this is scaling down. When you're scaling down, you divide your functions with the constant, and you will see that it's like you have an object, and then you press the object, and it will be going to look like this one. Okay, so that's what's happened when you are multiply, or basically multiply functions. Okay, multiply function with C or 1/C. And then the other one is when you multiply the y-axis, the y with negative. If you multiply with negative, you call this as a mirror. Okay, mirror. So mirroring. So when you read the questions, mirror the functions, then you need to multiply the y with the negative. Sometimes you can mirror across this x, right? Or mirror across this y, and it's becoming the left side. The left side, you will see that you multiply the x inside the functions here. Okay, and when you mirror across this x-axis, then means you need to multiply y with the negative. Okay, and how it looks like is basically like you are taking a mirror. Okay, so this is your original function, and all the size, everything will be the same. Okay, just a reminder for you. Okay, for transformations. All right, any questions here? No, I think it's quite clear, right? Okay. Okay, the other one here. This is essential functions that we are going to use. And maybe if you forget some of these functions, please review by yourself. Okay. So first, we have the linear function. Of course, the easiest one, just a line. Okay. And then the power functions, like x squared, the quadratic, the cube, and etc. We call that a power function. The root functions with the square root. Okay. There is an interesting part here. If you look at power and root, imagine these power functions, okay, and you rotate 90 degree. You rotate 90 degree, all the part of this power functions. Try to rotate all that functions 90 degree, the graph. You will notice that not rotate, mirror, sorry, not rotate, but mirroring. let me make. So this is, we have y equal x, okay, and this is also y equal x. So mirror all the things here, the power function with y equal x. You will see that somehow it will make this into this, and this into this. And then for this one, you will missing this, the other one here, this also. Keep in mind this will be in the next session after this one. Okay, this is because of the inverse. Okay, so root functions, and then we have also the reciprocal functions. Okay, reciprocal functions like 1 over x, 1 over x squared, and so on and so forth. This is also important to illustrate chapter 2 later, limit. Okay, and then exponential, logarithmic. I hope you still remember what this is. Okay, and then trigonometric. Yeah, this sine, cosine, tangent, all the property. I hope you still are familiar with. Okay, now as I mentioned before, we will talk a little bit about inverse. Okay, before we jump into the limit in chapter 2. Okay, so inverse. So basically, the word inverse is basically defined as exchange something, right? Exchanging. So in this case, okay, what are exchange, right? What? So we have domain, right, in our function, and we have range. So basically inverse, okay, we usually use these symbols, right, for a function, or just f with inverse, okay, which means this is a function that have been exchanged its domain and range. So domain become range and range become domain. Okay, that's a simple way to say it. But how we can make sure that a function can be inverse? That's the key questions. Okay, that's the key for understand the inverse. Okay. First, to be an inverse, you need to have one requirement. It's called one-to-one function. Okay, let me define one-to-one function first, and then we can define the inverse. Okay, a function f, let's say, is called one-to-one function if it never takes on the same value twice. That is whenever, okay, so this is the basically what it means by one-to-one function. Okay, so what does it mean is basically any x you find, let's say x1, x2. Of course, x1 and x2 is not the same. When you plug in x1, x2, so when you plug into the function, it cannot be the same. For example, the easiest one that we are familiar with, let's say, or maybe write this, just x squared. Okay. If you look at the x squared, the positive and negative part they have the same value, right? Because we only squared them and it will be a positive. For example, when x is 2, then f2 is 4, right? But when x is -2, this is also 4. So actually it's not one-to-one function, okay? But if you look at the graph, okay, if we take just positive, it's one-to-one function. If we look just a negative, it's also one-to-one. But if we take both of them into one whole function like this x squared, it's not one-to-one, okay? Right. So how to get, or how to check whether it's one-to-one or not? Aside from checking the numbers like this one, you can use, it's called the horizontal test, like this. So you see that it's crossing, right, more than one, right? So let me write here. To check, you can use the horizontal line test. So a function is 1 to 1. Yeah, horizontal line test. 1 to 1 if no horizontal line intersect its graph more than 1. That's why when you have a graph like this, it's perfectly fit with the horizontal line test, right? Because all the line here, they all just getting 1 point, right? Just crossing one point in the curve, okay? And that means it's one-to-one function, okay? All right, let me write in another slides to make some conclusion about the inverse, okay? So inverse, inverse. So let f be 1-to-1 function. Let's say we have domain A and range B, okay? Then its inverse function f inverse has domain B and range A, okay? And it's defined by okay, for any y in B. Why for any y in B? Because we already take the requirement that the function need to be one-to-one function. So we can have any y because it should be a one-to-one function, right? So basically, domain of f inverse become range of f, and range of f inverse become domain of f. Okay, and also remember, because I'm writing the inverse as f with power of -1, it seems, right? This is not the same, okay? Different, okay? And how to find practically the inverse. Let me use another slide, okay? Or do you want to look for this one first or later? I will upload later, okay? In the video, you can check later. And right here, I think this is, I think you already know, right? The inverse is the x with the power of 1/3. Okay, and if you look for how it is done, and it's true that it's become x. Okay. Okay. Practically, for finding the inverse, so first write in terms of x and y. So y equal x cubed. Okay. And then you need to exchange x and y, and then you need to make x in terms of y. And practically that is the inverse. And then as you exchange one more, okay, that's how you are doing the inverse. Okay, another one. Maybe I'm writing here. Let me make this a little bit smaller. I'm writing too big. Resize. Okay, we're right here. Because we have this as our definition for the inverse, we can also develop another relations. Okay. Okay. This is for every x in A, for every x in B. Okay. And B is the domain and range that we have set previously. Okay. It's basically, if you look at the function, and then let me right here. The function, okay, f, and then you get the function here, okay, and then you are going to have another one here. Let me use a red now, going inside. Let's say this is an f inverse, and what the product is, it will be going back to the x. Basically, because f inverse is the exchanging the domain and range, so x going to be a functions, you get a function of x, and you put the undo. So it's like an undo, right? You're undoing your f, your function. undo, and then it going back to be an x here. Okay. Sometimes this inverse can be useful for simplify some looks like a complicated function. You can simplify if you look for the inverse sometimes, and help you in several cases in especially in derivative. Okay. Okay, maybe one more thing about inverse, and then we can move on to the limit concept. Okay, one more thing here is the graph. Okay, so the graph f inverse obtained by reflecting or mirroring graph of f about line y equal x. Okay, so let me make this. Let me make the line, and if this is maybe here, so the other one will be around here. Yeah, is it the same? Yeah. Okay. Let's say this is y of f of x, and this will be f inverse. Okay. Okay. Now back to the x squared. Okay. Back to the x squared. I'm telling you that y equal x squared. If you draw and you learn that from the symmetry, it's not one-to-one. But I'm said that if you just take one part of it, left or right, we can make it one-to-one. And that's precisely, if you remember back in the day, you learned that there is an inverse for sine. Let's say this is alpha, or maybe sine inverse, or maybe or x. Okay, cos inverse x, tangent inverse x. If you remember sine and cosine, wait, at least it will be continue, right? Like they have peak the same peak, right? But you know that it has the inverse. What should you do? This also, what should you do? You know that this is similar to the square root of x, right? Yes, you need to restrict the domain. Restrict the domain. At least when you see the domain until here, you get one-to-one functions, right? Only here. Okay. So restrict the domain. This is also restrict the domain. So let me write here. We can restrict the domain. Sometimes many students forget about this fact. Okay, restrict the domain. So because we already know that we can have this inverse of the trigonometric, and then we can have this inverse like this one, we forget what happened with the domain, because this is already a fact, right? We already use it for calculation. We already use it for proving, or use it in engineering problems, right? But the fact is, we need to restrict the domain first. Okay. All right. I think that's the additional part for the inverse, and I think that is actually chapter 1. So chapter 1 is actually not really that heavy subject. It's more of review, and it's actually having the other, like for example, it still has the This function models, exponential, logarithm, but I'm skipping all of that. I will teach the exponential and logarithm when we are dealing with the derivative, before we going to drift to derive some functions related to log and exponential. I will maybe give you a little bit what you need to be prepared for exponent and logarithm. Okay. Now we can move on to the yeah, I think we can go to limit and derivative. So first is the tangent and velocity problem. Okay, so we have a tangent and velocity problem. That's the the title, the very beginning of limit. Okay, so before we learn what limit is, let me tell you about the tangent first. Okay, tangent. Okay, what tangent means. Okay, so tangent is actually the meaning of the tangent is to touch, something, to touch. So when you're telling, or maybe if you remember in high school, if you learn calculus, find the equation of tangent line. Okay, equation or tangent line. So this is just a random example. So maybe here, okay, you have P. Okay, usually equation of tangent line at P, and then P equals some coordinate, right? And you find the gradient, you put the gradient inside, you find the line, right? Okay. If you look here, the tangent means you have a curve like this. Let me make it bigger. At one point here, there is certain line that is passing through. But because my writing here, my drawing, the pixel is too big to be written, so it seems not really one point, right? But in reality, the tangent means the line touching the blue curve is exactly 1 point. Okay, and usually in your textbook it's usually at P. Okay? So that's the tangent. Okay, it's from the Latin. Yeah, I think Latin words, right? Like for example, you have the circle, and you find the tangent here, right? If you have another line like this one, like cutting this circle, like maybe this is A, this is B, this line is called a secant line. Okay, if you heard this before, this is what it means. It's to cut, okay, to cut the line. The secant line. Okay. Okay, let me go through let me go through the website, the GeoGebra, so you can see what it looks like if you have it. So let me stop this presentation for a while, and let me present the other website. Okay. All right. Okay, I hope you can see the GeoGebra. Okay, you can see the GeoGebra. Okay. This is the GeoGebra Classic. So if you are going inside the GeoGebra, you can use the GeoGebra Classic by pressing you can select at the beginning, not directly graph calculator, but select the classic tools. But actually, it's the same thing. So we can put our function here, we can literally write many things. And in the left corner, we can see the calculators. This is all the, if you need to write interval, you need to write notable function. For example, we can start just write the x and then squared. That's pretty much what we have done here. This is the x squared functions. Okay. And let me write some point, and then pick point. Okay, pick point maybe here. That's my point A. And let's draw the tangent line. You can select this, and you can select, there's a lot of tools. So if you want to make some graph, and maybe you look for questions in the textbook, and then you want to know how it looks like visually, you can use the GeoGebra, and you can draw by yourself, and then look for maybe you got idea with the questions you have. Yeah, let's try to write or draw the tangent here. Draw the tangent in here. Let me make it bigger. Okay. Okay, let me make bigger there. Okay. Okay, wait, I need to make. Okay, why it's not visual? Okay. Oh, let me make another point. Sorry. Maybe I will put the point later. Let me put directly the tangent. Okay, maybe putting here. Okay, wait. Put here. Okay, let me make the line first and make the tangent. Okay, so that's my tangent. Let me make another color and make blue. All right. Okay, so the brown is the functions. A and B is just a line. Let's say this is our second line. I will use this line later in the further section of limit. And the blue line is our tangent at A. Okay, so this is the tangent. Let me copy the graph first. We are going to use this graph in our notes. Okay, let me move to. Let me move the picture first. Okay, all right. Okay, we can, I think, stop here, and we will go back later for another graph. I hope you can try by yourself the GeoGebra. It's quite interesting and fun. Sure. All right. Okay. Okay. We can start again. Okay. Okay. So here's the deal. This is our tangent here at point A. The tangent, right? Now, if you look here, actually we can. I mean, where is this per first? We can actually look for if we take this and if we take this line B here, okay, if we are seeing the not I think not B, let's just say we have this triangle here and we have the delta. We can also saying that the tangent here it will be delta y divided by delta x. Okay, and of course you can relate this to triangle trigonometry, and you have the sine, cosine, and tangent, right? But for this case, look for the tangent here. And usually, later in limit, you need to imagine what will happen when you are moving the point. Okay, so imagine you have this point A here, and you are moves this point, move alongside the curve, along the curve. Okay, and when you look at the tangent will be changing, right? The tangent will be changing. The line will be changing. Maybe here will be here like this, maybe like this, right? Up until you find B. Okay. But still, we are not really sure what we are doing here. Why we need to get close A and B. Okay. So here's the deal for the limit as introduction. So limit is basically a concept. Okay. So it's basically a concept. Let me just write a concept of getting closer. Okay. How close? It's really, really close. Okay. So we can maybe if we have the let's say we have another curve. Maybe I will check with the other slides first. Okay. So let me draw another one. Okay. And just imagine this is the okay, imagine this is the x squared. Okay. Let's say we have the make another color blue. Maybe this is our, let's say this 1 and 1, and maybe here. Let's say this is our 1 point here. Okay. And another point, maybe here, we have Q there. Okay, let's say this is 1.1, and we don't know the point in Q here. Let's say we have x squared, okay, because our function is x squared, okay. And how to find the equation of tangent line? I believe you still remember how. So find equation of tangent line to the function, or to the y equal, let's just say y is a function, y equal x squared at p1, 1. Okay. So we can start by taking the gradients, right? Taking the gradients. So let's say this is the tangent, right? And this is the triangle. Or let me translate to here. Okay. Let's say just this small triangle here. So this will be P, okay, P11, and I don't know this. Let's say delta y and delta x. Now what I want to do is I want to look for this delta first. Okay. So we can start with assumptions. Okay. So let's assume the delta is really small, right? For example, to find the equation of tangent line, first, at least you know to find, you need to find the m, the gradient. Okay. So the gradient will be x squared minus 1, right? At least if you look here, if you take a look this gradient here from here, we take a look here. Okay, let's just write that first. Okay, let's just write that first. Divide by x. Okay. Now it can be in anywhere, this q. Okay, so it can be here, it can be here, it can be here, right? Or it can be here. Okay. Now let's start with if you have 1, it will be not really good, right? It's 0 over 0. So let's start with 1.1. So let's start with 1.1. What will happen with the gradient? You will have 2.1. Check again another number. Let's make it smaller. So let's put some 0. So 1.01. Okay. What will happen? This will be 2.01. And check again. And you get 2.001. And every time you add the 0 inside this decimals here, then your gradient will be 2, and it add more 0 here, right? 0, 0, 0, maybe you get bigger like that. Okay. That's the first case for 1.1, and you increase little by little. Now, how about we decrease 1 little by little? Okay. We can start with the 0, and it's just 1, and it's not really meaningful. But when we are going to put this x nearby 1, okay, 0.9. Okay, so what I mean is, if you look this is x squared. So if this is 1, 1, so this is 1. What I want to do is I want to find some delta here and some delta here that is really, really small. Okay. So probably I will start with 999 here, and then this will be 1.00001, right? And something, and you can add 0, and you can add 99, right? So what will happen here when you add 0.9, you get it's around 1.9. And when you get 999, you get 1.999. And when you increase 9, when you add 9, you add more 9, and you get more more 9 in the gradient. When you look the number here, 2.0001 and 1.99999. So this will be really, really close, okay? Really close with number 2. So I will say, in this case, both are closer to number 2, right? But can we say the gradient is 2? We cannot say that, right? We cannot say. We cannot say that this is exactly 2. No. We need some concept to make this happen. And that is limit. Okay. Okay, another example on how we are going to look this through. Because sometimes when you're thinking limit, you are not thinking the small point that is important in limit. I will show you later what I mean by that. Okay? But let's get to another example. You have a ball, okay, and you drop the ball, okay, from a very high place. Let's say maybe 400 meters here. But actually the height is not really matter, right? So you drop the ball, not really throwing it, just dropping the ball. And you need to find velocity of the ball after 5 seconds. And you have the distance function as s with a variable t. You have 4.9 t squared. Okay. So what is the problem with the question here? You need to find the velocity, but there is no time interval, right? That's the important thing here. No time interval. So what will happen? We cannot really sure what will happen with 5. Well, maybe if some of you are thinking, oh, we can just derive it, but this is not yet derivative, so we need to take this really in a pre-derivative calculations. Okay, so what I mean is we have average velocity is the same or equal with the change in position, if you remember physics a little bit, and how much time elapsed, right? Or just time is okay. First is, let's say we have 5 seconds, right? Let's say we have 5 until 5.1. So we have 0.1 time for the elapses, okay? For the time to be elapsed. So change in position. So we are going to put in the t inside the function s, and the time elapsed just 0.9 0.1. Sorry. And if you calculate this with your calculator, you will get 49.49 meter per second. Okay. Seems nice, right? But we have this is just one interval here. Let's try other interval. We can try. So let me write here my conclusion here, my calculations. The first interval here is making 4949, the velocity. Okay. Let's make the interval shorter. Let's make shorter. this become, okay, and make it shorter, and still it looks like similar, right? So when it's getting close, so when it is closer to 5, okay, so when t is closer to 5, okay, this velocity is closer to 49. So we can also write down a new terms for you, or maybe you have heard before. It's called the instant velocity or instantaneous, okay, velocity. So what does it mean? So it means that the velocity that it is happening instantly after 5 seconds. So instantly after 5 seconds, it's happened. And it will be around this much. And because still, if you see the number here, it's not the same as 49, but it's close, right? It's close enough. When you add more zero here, it's getting closer, but it's not 49. Do you get it? If you want to make it into 49 here, that's when you need limit. Okay, that's when you need limit. So we need limit to say that, okay, this is the velocity. Okay, I hope you get the idea of the limit. I hope you get the idea. So limit is something that is really, really close, but it's not the exact same one with what we have looking for. Like the if you know the Zeno paradox, but I think that's for calculus too. But yeah, that's still okay. So you have the wall. You have a person here. The person want to run into the wall, but there is requirement. How he walk or how he run. So for example, he run maybe 1 meter. Okay. The next time he need to walk, he needs to walk half of the previous one. So 0.5. And the next part is also half from before. So half, so 1/4, right? And then 1/8. Can he reach the wall? Can he reach the wall, the person here? I don't think so, right? He will not reach the wall, but it's getting closer to wall. But in limit, the person touched the wall. We can consider that in limit. I put some quotations so that it's you need some terms to be applicable. Okay. Okay. I hope you get my idea. All right. Now, one example for what limit is. Okay. Imagine you have circle, and then you have you put some put not put a polygon in a circle. So polygon is anything, any geometry that has more than at least 3 sides. Okay, at least 3 sides. So from n equal 3 until some n equals something. Okay, n equal 3 is just a triangle, right? A trigon, right? So let's draw the triangle. All right. Now, if I write the area of triangle, what it is, it's just half, and we can say this is the base, this is the height here. So base and height is the area of triangle. And we also have this from the center to this part here. Let's say this is A, B, and O, and we have the radius here. Okay. What happened when we are increasing the n? Increasing the n. So we increasing the n. For example, we have okay. We have a lot of, actually it's a lot of triangle here. It's a hexagon here. Okay. So it will be n equals 6. What's happening when I'm increasing to 8 to 12? Okay. If you look at how it looks like here, it seems that the sides here, the sides is getting closer to the circle, right? It's getting closer. All right. And when we are getting closer, the area polygon, the area will be half A, B, and N, right? AB, oh yeah, ABO here. Let me write AB here, ABO. Oh, forget the height, sorry. So this will be height. Or maybe this should be the same. Let's say this AB height, okay? So the area will be this formula, okay? So when n is getting larger, it should be getting closer to the circle. What's the area of circle? Area of circle is, or maybe circle, pi r squared, right? So can we prove that? So limit as, let's say that this is the r, this is the h here. Okay. You see that the h, if we are going to increase the number of n, it will going to reach this circle, right? So the h is getting closer to r actually. And so I can write this limit as h getting closer to r. And then if you look at, let me write here, half AB, N, and H. What is ABN? AB is the sides, and N is the number of the sides, right? So AB is 1. Let me write here. So 1, 2, 3, 4, 5. It's 6, right? So 6 AB. But imagine the 6 is going to be closer to the circle. So the sides of polygon, so sides of polygon, we're getting closer to a circle. Circle, circumference. Okay. What is the formula for circumference for the circle? Is just 2 pi r, right? That's why we can write this in terms of 2 pi r and h. Okay. And then we can exchange this limit with this, and then we can have pi r squared. Okay. So that's how you are actually implementing limit. It's actually helping you to solve some numerical problems, geometry. And if you need some approximations, you can also use limit to help you better understanding, better visuals, right? Okay, sorry if you have a little bit confusion about here, but what I was doing here is I want to prove that when I was having a circle and having a polygon inside the circle, when you increase the polygon, when you increase this triangle from triangle, maybe increase, and then you have a polygon that's really, really close to a circle. And when you're doing with limit concept, you can have a circle from the polygon. And it was true when we are dealing with the concept. Okay. Okay. Now another one. What I want to show you is okay. Let me go back to the GeoGebra. Okay, the GeoGebra, and let's make some another graph. Okay, another graph. Okay, let's delete this. Okay, let's make another interesting function for you. So let's make okay. All right. Now we have x minus 1 and x squared over x squared minus 1. Okay. Now probably you're curious why I'm looking at this function here. Actually, it can be any reciprocal function, but I want to show you when you put x equal 1. Okay. When you put x equal 1, what will happen here? With the function, you see the function on the left, x minus 1 over x squared minus 1. What will happen there? It's 0 over 0, right? But you see the line is just a line, just curve. What happened? Anyone know? You know that it's 0 over 0, right? There's that is it's actually not simplified, Rian. It's actually the real situation. So what I want to show you is, let's see this one here, the x equal 1. Let's see on the curve, it's around this part. Let's get zoom in as much as we can and see whether it's getting anything weird or not. But still, it's 1 here, getting closer, okay. Still, we are getting closer. Zoom in. Okay. What will happen? Okay. Wow, really, really. Okay. I think I've seen something here. Anyone seeing something really strange? The line? Yeah, of course, in reality, there is a hole at x equal 1. So what I want to show you is, where is the hole? Oh, wait. My laptop is laggy. Wait. Or you can try, yeah, page unresponsive. Oh, I'm zoom in too much. Let me check whether you can see or not. If you see the one there, it's actually there is a discontinuity here. So it's the curve is actually showing you the real situations. So what we are doing in our paper, we are putting dot the discontinuity. That is the simplified one, not this curve. This curve is showing you the real functions. Dot 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 dot, right? So let me check again whether it's still. Oh, it's still okay. Wait. Okay, let me. Okay, I think I can give to you what has happened. Uh, maybe I need to wait. Let me stop presenting first. Okay, wait for a minute. Okay. Okay, let me try myself, and then I will show you later. Wait. Okay, I see now. Okay. All right. So if you see, then you can trust. Okay, see at the x equal 1. You see? That's discontinuity. Okay? So in reality, because of the limit is uh, there are discontinuity there, but because we are looking point by point by point, in terms of reality, we are not seeing any hole or any discontinuity. Okay, but actually there is one there. Okay, and yeah, in limit, if you have discontinuity, you still have a limit, right? So let me go back to my notes and we can have some idea on the limit itself. All right. Now, this is the last thing for today's class. So imagine this is what we have done before. Uh, this is the hole should be here, right? Should be in one. Let's say one. The hole should be here. So we are getting hole here. So the one who are simplified the functions are us, not the computers. The computers, they are using the real exact problems. Okay, so let's say this is our function here, x minus 1, x squared minus 1. Okay, we say that we are going from here, It's getting closer to 1 point here, and it is around 0.5. If you look at the previous GeoGebra graph, okay, it's getting 0.5. Okay, if you are put number 1 there inside our functions. It's become undefined, right? But if we write in terms of limit, approaching to 1 of our x minus 1, x squared minus 1, from the graph, okay, we get it's getting 0.5. And actually it's true, it's 0.5. So we can try to going to here. So maybe 0.9999 and maybe 1.00001. Okay. And we got this limit. All right. Then we got some definition here. So limit is going to be some number L. F is defined when x is near number A. So this should be the requirement for limit. So, and then some open interval having A except not at A itself. So this is true from our previous example here. We can find the limit here. But at that point, at x equal 1, it's undefined, right? Okay, so that's pretty much the introduction to limit. Okay, so the next session we'll be having more discussion, especially for in limit. And I hope you get my point, what limit is, and from the beginning, a little bit of functions, a review about functions, inverse functions. Have you still remember? Okay, last part of today is actually another small quiz. So you can prepare any, if you have papers, phone, pen, paper, smartphone for scanning the QR code. Okay, are you ready? Okay, let's get ready to scan the QR code. Let me make it bigger here. Okay, scan the QR code, scan the QR code. All right. Okay. 13, 14. Okay, let me use my screen and I will show you again one more time. Okay. If you have trouble to join the QR code, you can go to this website, menti.com, and you can enter the code, the number you see on the screen. All right. Okay, I think around 7, 8 students. So for the or maybe 7 students more. 7 students, yeah, 7 students. Okay. Okay, ready? Okay, I think 6 more. 6 more. Oh. Okay. That's okay. This is just as a small quiz, not really a quiz. It's just a small fun quiz. Okay. Okay, I will start now. Okay. Which of the following statements that is false based on the picture of the function? You need to see your phone. Okay. Okay, sorry. Okay. Okay, yeah. Sorry. Okay, get ready. Okay, next part. Sorry, I don't know. Before I was logged out accidentally. I don't know why. So yeah. Okay. Ready? I will start the games. Okay. Okay, that's the statement. There's two statements. Which one is? Uh, there are four options. Please choose. All right. Okay. It's just testing whether you are got the right assumption or not. Three, two, one. Okay, time's up. Okay, good. Most of you are getting the right answer. Both false. Okay, let's move to who are getting. Oh, congratulations. Okay. Okay, get ready. Another one. All right. Number two. Okay, let's start. Yeah, you need to if you want to write, but I don't think you can. I don't think you need to write like really long, right? I believe 15 or 20 seconds is enough. I'm giving more time for you to choose the correct one. Okay, 25. All right. Okay, 7, 6, 5. Okay, just randomly answer. Randomly answer. 3, 2, 1. Okay, what is the answer? All right. Nice one. Okay. It's A, the answer. Whoa. Nick, you become the champion for the quiz. Okay. Congratulations. All right. So this is the end of our course, and see you on Thursday. Okay. So yeah, life is tough, but we need to keep going on. So see you on Thursday, and keep on going. All right. Yeah, you can leave the Google link if you want. And if you have any discussion left and you want to ask something, you can ask if you want. But if not, then you can just leave. And see you again next Thursday. Yeah, you're welcome. Yeah, bye. Yeah, see you again. Don't forget, you have a TA class. Okay, after this, you have the TA class. Yeah, TA links for your teaching assistant. So you have TA session with your teaching assistant. We have two TA in this course, the GDEP and the IITP and College of Engineering. Okay, so bye and see you again.